Picture this: a darkness so powerful it swallows entire stars, a force so immense it bends the very fabric of space and time. Now imagine that monster lurking not just anywhere, but at the edge of everything we can see, billions of light years away. These aren't just black holes, these are the universe's oldest, most distant giants, and they're hiding secrets that could rewrite everything we know about cosmic history. Today, we're diving into the abyss to uncover 50 mind-blowing facts about these faraway cosmic titans. How do we even detect something so impossibly distant? What do they tell us about the birth of the universe, and why do some of these black holes defy the laws of physics, growing bigger than entire galaxies while the cosmos was still in its infancy? From quasars brighter than 1 trillion suns to black holes that might be older than time itself, we're about to explore the farthest, most mysterious corners of space. So buckle up, because by the end of this journey, you'll see the universe in a way you never thought possible. Let's begin. Now, let's zoom in on the record holder itself, the farthest known black hole ever detected. Meet ULAS J1342+0928, a supermassive beast lurking 13.1 billion light-years away. To put that into perspective, this black hole existed when the universe was just 690 million years old, a mere 5% of its current age. What makes this discovery so groundbreaking? For starters, its sheer size defies logic. This black hole weighs in at around 800 million times the mass of our Sun, a staggering number that left scientists scratching their heads. How could something so massive form so quickly after the Big Bang? The answer lies in its host, a blazing quasar, one of the brightest objects in the cosmos. The quasar's intense light, powered by the black hole's insatiable appetite, acted like a cosmic beacon, allowing astronomers to spot it across unimaginable distances. But here's the real kicker: its existence forced us to rethink how black holes grow. Traditional models suggested these giants took billions of years to form, slowly feeding on gas and stars. Yet ULAS J1342+0928 proves some black holes grew at breakneck speeds, possibly from colossal gas clouds collapsing directly into black holes or merging with others in a violent cosmic frenzy. This discovery didn't just add another entry to the record books, it tore up the old rulebook entirely. Suddenly, the early universe wasn't just a quiet nursery for baby galaxies. It was a chaotic, high-stakes arena where black holes could become monsters almost overnight. And if this one exists, who knows what other ancient giants are still waiting to be found? Now, let's pull back the curtain on how astronomers actually spot these cosmic giants from billions of light-years away. It's not like we can just point a telescope and see them directly. Black holes are invisible by nature. So how do we find them? The answer lies in their side effects and the clever tricks of modern astronomy. First up, redshift. When light travels across the expanding universe, its wavelengths stretch, shifting toward the red end of the spectrum, like a cosmic Doppler effect. The farther away an object is, the more extreme this redshift becomes. By measuring how much a black hole's light has stretched, astronomers can calculate its mind-boggling distance. ULAS J1342+0928, for example, has a redshift of 7.54, placing it firmly in the universe's toddler phase. But redshift alone isn't enough. Enter X-rays, the telltale screams of matter being torn apart. As gas spirals into a black hole's accretion disk, it heats up to millions of degrees, blasting out high-energy X-rays. Space telescopes like Chandra catch these signals, turning invisible monsters into detectable targets. Combine that with the blinding glow of quasars, and suddenly, even the most distant black holes can't hide. Then there's gravitational lensing, Einstein's cosmic magnifying glass. Massive objects like galaxy clusters bend spacetime so much that they distort and amplify light from objects behind them. This natural telescope lets us spot black holes that would otherwise be too faint to see. It's a cosmic detective game, piecing together clues from light, energy, and space-time itself. And with every new tool, from next-generation telescopes to artificial intelligence sifting through data, we're getting better at uncovering the universe's best-kept secrets. Now, here's where things get even more fascinating. Quasars are the universe's ultimate powerhouses, and they play a starring role in our hunt for distant black holes. Imagine a supermassive black hole with an insatiable appetite, gobbling up gas and dust at an unbelievable rate. As this material spirals into the black hole's accretion disk, it doesn't just vanish quietly, it puts on a show. The friction and heat generate so much energy that the quasar outshines entire galaxies, blasting light across the cosmos like a lighthouse cutting through fog. That's why quasars are such a game changer. Even when the black hole itself is billions of light years away, the quasar's brilliance makes it visible to our telescopes. It's like spotting a single lit match in a dark forest, except this match is brighter than a trillion suns. The light from these quasars travels for eons, carrying clues about the black hole's size, hunger, and even the conditions of the early universe. But quasars aren't just bright, they're also incredibly precise tools. By studying their spectra, astronomers can decode the composition of the gas swirling into the black hole, measure its redshift, and even track how fast it's devouring matter. Without quasars, many of the most distant black holes would remain hidden in the cosmic shadows. So next time you hear about a record-breaking black hole discovery, remember, it's often the quasar's dazzling light that led us there. And speaking of light, let's talk about how these distant black holes are essentially time machines, giving us a glimpse into the universe's infancy. Here's something that will bend your mind even further when we observe these distant black holes. We're not just looking across space, we're peering back in time. Light takes time to travel, and the farther away an object is, the longer its light has been journeying through the cosmos to reach us. That means the light from a black hole 13 billion light years away shows us what it looked like 13 billion years ago, when the universe was just a fraction of its current age. Think of it like flipping through an old photo album of the cosmos. The most distant black holes act as snapshots of the universe's earliest chapters, revealing conditions that existed mere hundreds of millions of years after the Big Bang. Their light carries clues about the raw materials floating in space back then, the density of matter, and even the temperature of the infant universe. But here's where it gets even wilder. Because the universe was so much smaller and denser in those early moments, black holes had an all-you-can-eat buffet of gas and stars to feast on. That's why some grew so massive so quickly, defying our expectations. By studying them, we're essentially uncovering the cosmic recipe for how the first giants of the universe came to be. And just like time travelers, astronomers use these ancient black holes to piece together the story of how galaxies formed, how the first heavy elements were forged, and how the universe evolved from a hot, dense soup into the vast web of galaxies we see today. Now, let's tackle another puzzle: how some of these early black holes became so enormous so fast, a mystery that still leaves scientists scratching their heads. Here's the real head-scratcher: some of the earliest supermassive black holes we've found are absolute monsters, weighing in at billions of times the mass of our Sun. And that's the problem. According to everything we know about how black holes grow, these cosmic giants shouldn't exist so early in the universe's history. Think about it like trying to grow a skyscraper overnight. It just doesn't add up with the usual rules. Normally, black holes start small, maybe a few dozen times the Sun's mass born from collapsing stars. They grow over billions of years by gobbling up gas, dust, and even other black holes. But the ones we see in the distant universe, they skip the line entirely. By the time the universe was just a few 100 million years old, they were already fully formed behemoths. So how did they get so big so fast? One theory suggests they might have started as seed black holes, primordial giants born directly from collapsing clouds of gas in the chaotic early universe, bypassing the star stage entirely. Another idea is that they feasted on an ultra-dense buffet of matter, growing at breakneck speeds thanks to the crowded conditions back then. But here's the kicker: even these explanations stretch our current models to the limit. If these black holes grew by eating, they'd need to consume matter at impossible rates, faster than physics typically allows. And if they started as seeds, we're still not entirely sure how those seeds formed in the first place. This size paradox isn't just a curiosity, it's a glaring gap in our understanding of cosmic evolution. Solving it could rewrite the rules of how black holes and even galaxies are born. And with new telescopes like the James Webb peering deeper into the past than ever before, we might finally get some answers. Now, let's push even further, to the very edges of what we can see, where these distant black holes test the limits of our cosmic horizon. But here's something even more mind-bending: these ancient black holes don't just challenge our understanding of size and time. They also force us to confront the very boundaries of the observable universe itself. Picture this: the cosmic horizon is like the ultimate edge of our vision, the farthest point we can possibly see. It's not a physical barrier, but a limit set by the age of the universe and the speed of light. Because light takes time to travel, every glimpse into deep space is also a look back in time. The most distant black holes we've detected sit so far away that their light has been journeying toward us for nearly the entire history of the cosmos, around 13.8 billion years. But here's where it gets tricky. The universe isn't just expanding, it's accelerating. That means the space between us and those far-off black holes is stretching faster than light can bridge the gap. Some of these objects are already so distant that their light will never reach us in the future. They're vanishing beyond our cosmic horizon, like ships sailing over the edge of the world in ancient myths. This expansion also means that the black holes we can see today are even farther away than their light travel time suggests. Take that record-breaking quasar, ULAS J1342+0928. While its light took 13.1 billion years to reach us, the actual distance to it now, thanks to cosmic expansion, is a staggering 30 billion light-years. Wrap your head around that. We're seeing it as it was in its youth, but today it's practically in another universe. And yet, these distant black holes are more than just cosmic milestones. They're probes into the universe's most extreme conditions, testing the limits of physics itself. By studying them, we're not just exploring space, we're peering into the very fabric of reality, where the rules we know might bend or even break. Now, let's turn our attention to another puzzle: how these ancient giants might be tangled up with one of cosmology's greatest mysteries, dark matter. Now, let's untangle one of the most intriguing cosmic mysteries: how these ancient black holes might be whispering secrets about dark matter. Dark matter is the invisible glue holding galaxies together, making up roughly 85% of the universe's mass. Yet we've never directly seen it. It doesn't emit, absorb, or reflect light, hence the name. But here's where distant black holes come in. Some theories suggest these cosmic giants could be tangled up with dark matter in ways we're just beginning to grasp. One idea: dark matter might have helped seed the earliest black holes. Imagine the young universe filled with dense clumps of dark matter, acting as gravitational traps for ordinary matter. Gas and dust could have collapsed around these invisible scaffolds, supercharging the growth of the first black holes. That could explain how they grew so massive, so fast, dark matter giving them a head start in the cosmic race. There's another wild possibility: primordial black holes themselves might be dark matter. These hypothetical black holes, smaller than stars, could have formed in the chaos of the early universe. If they exist in vast numbers, they'd be invisible yet massive enough to account for the missing gravity we attribute to dark matter. Distant supermassive black holes might then be the rare giants that grew from these tiny seeds. But the plot thickens. Some models suggest dark matter particles could collide and annihilate near black holes, releasing energy that lights up their surroundings. If true, the most distant black holes might be indirect dark matter detectors, their extreme environments revealing clues about this elusive substance. Of course, this is all speculation for now. Dark matter remains one of cosmology's biggest puzzles, and distant black holes are just one piece of it. But every discovery at the edge of the observable universe brings us closer to answers, or perhaps even bigger questions. Next, let's see how Einstein's genius helps us spot these cosmic ghosts through a phenomenon called gravitational lensing. Here's how Einstein's cosmic vision helps us spot the unseeable. Gravitational lensing is like nature's magnifying glass, courtesy of black holes bending space-time itself. Picture this: light from a distant galaxy travels toward us, but on its way it passes near a supermassive black hole. The black hole's immense gravity warps space, twisting the light's path like a funhouse mirror. That distortion can magnify the background galaxy, making faint objects suddenly visible to our telescopes. This isn't just theoretical. Some of the most distant black holes we've found were revealed because they lensed light from even farther galaxies behind them. Without this effect, those background galaxies might have stayed hidden. But thanks to Einstein's 100-year-old prediction, we get a 2-for-1 deal. The black hole's gravity betrays its presence, and it hands us a free cosmic zoom lens. The wildest part, lensing can create multiple images of the same galaxy, stretched into arcs or even perfect rings like a celestial mirage. Astronomers hunt for these distorted patterns to map invisible black holes lurking in the darkness. Next up, we'll meet the oldest black hole ever found, a relic from when the universe was just a toddler. Now, let's turn our attention to a true cosmic fossil, the oldest black hole ever discovered. Nestled inside the galaxy GNZ11, this ancient behemoth existed when the universe was a mere 400 million years old, a blink in cosmic time. What makes this black hole so baffling is its size. Despite the universe's youth, it already weighed in at millions of times the mass of our Sun. That's like finding a fully grown elephant in a nursery. It shouldn't be possible under our current models. Scientists are still scrambling to explain how it grew so big, so fast. Did it form from the direct collapse of primordial gas clouds, or did it feast on surrounding matter at a rate we've never seen? GNZ11's black hole isn't just a record breaker, it's a time capsule. Its existence forces us to rethink how quickly structures emerged after the Big Bang. If black holes this massive existed that early, the early universe might have been far more dynamic and chaotic than we ever imagined. Up next, we'll explore how these ancient monsters fueled their incredible growth. Hint: it involves a feeding frenzy unlike anything in the cosmos today. Now picture this: a cosmic buffet unlike anything we see today. The most distant black holes didn't just grow, they feasted. In the early universe, these monsters gorged themselves on gas, dust, and even entire stars at rates that would put modern black holes to shame. Think of it like a wildfire. Today's black holes nibble at their surroundings, but back then, they were engulfing matter so fast, their accretion disks blazed with temperatures in the millions of degrees. Some devoured the equivalent of a sun's worth of material every year. That's 1,000 times faster than the supermassive black holes in nearby galaxies. Why such insatiable appetites? The early universe was a denser, more chaotic place. Gas clouds were everywhere, and without fully formed galaxies to stabilize things, matter funneled into black holes with terrifying efficiency. It's like dropping a sponge into an ocean. Absorption happens instantly. This frenzy didn't last forever. As the universe expanded, the buffet thinned out and black holes slowed their roll. But for a brief, violent window, these ancient giants ate like kings, and their leftovers, the blazing quasars we see today, are the crumbs of their epic meals. Coming up, we'll dig into the biggest mystery of all: how these black holes got their start in the first place. Were they born massive, or did something supercharge their growth? Stay tuned. Now, let's tackle one of the biggest puzzles in astrophysics. Where did these ancient black holes even come from? The mystery of seed black holes has scientists divided, with two leading theories battling it out. The first idea suggests they were born from collapsing gas clouds in the early universe. Picture a massive, pristine cloud of hydrogen, untouched by stars or galaxies. Under its own gravity, it could have collapsed directly into a black hole, skipping the star stage entirely. These so-called direct collapse black holes would have started out heavy, maybe tens of thousands of times the Sun's mass, giving them a head start on growing into the monsters we see. But there's another camp that argues the first seeds were stellar corpses. The universe's earliest stars, called population 3 stars, were giants hundreds of times more massive than our Sun. When these behemoths died in violent supernova, their cores could have collapsed into black holes. The catch: even the biggest stellar black holes would have started small, only a few dozen solar masses. That means they'd need to grow absurdly fast to reach supermassive sizes in just a few 100 million years. So which is it, gas clouds or star remnants? The truth might be both. Some seeds could have formed one way, others the other. Or maybe there's a third, even wilder option we haven't thought of yet. What's clear is that until we peer even further back in time, perhaps with the James Webb telescope, this cosmic whodunit remains wide open. Up next, we'll see how telescopes like Chandra have been our eyes in the dark, spotting X-rays from black holes at the edge of space and time. Turning our gaze to the tools that make these discoveries possible, let's talk about the Chandra X-ray Observatory, a game-changer in our hunt for the universe's most elusive black holes. Unlike optical telescopes, Chandra specializes in detecting high-energy X-rays, the telltale signature of black holes devouring matter. When gas spirals into a black hole's accretion disk, it heats up to millions of degrees, blasting out X-rays that travel across cosmic distances. Chandra's sharp vision can pinpoint these faint signals even from black holes billions of light-years away. One of its biggest breakthroughs, catching X-rays from quasars like ULAS J1342+0928, the distant black hole we discussed earlier. Without Chandra, we'd miss these cosmic breadcrumbs, the only way to confirm a black hole's presence when it's too far for other telescopes to see. It's also helped map how supermassive black holes grow over time, revealing that many were already giants when the universe was just a toddler. What makes Chandra so powerful? Its orbit high above Earth's atmosphere, which blocks X-rays, and its precision mirrors that can focus these high-energy photons like a cosmic magnifying glass. Next time you hear about a distant black hole discovery, chances are Chandra played a starring role. And speaking of cosmic detectives, wait until you hear how the Hubble Space Telescope added its own pieces to this puzzle coming up next. Now, let's unravel one of the universe's most fascinating partnerships, the deep connection between supermassive black holes and the galaxies they call home. These cosmic giants aren't just passive residents, they actively shape their galaxies in ways that defy imagination. Picture this: as a black hole feasts on surrounding gas, it doesn't just grow, it sends out powerful jets and radiation that can heat up or even blow away nearby star-forming material. This means a single black hole can put the brakes on an entire galaxy's ability to create new stars, effectively controlling its evolution. But here's the twist: it's a two-way street. Galaxies also feed their central black holes, funneling gas and stars toward them through gravity and cosmic collisions. The largest galaxies we see today, like our own Milky Way, likely grew alongside their black holes over billions of years. In fact, astronomers have noticed something striking. The more massive a galaxy's central bulge of stars, the more massive its black hole tends to be. This tight correlation suggests they grew together, locked in a gravitational dance. Some of the most distant black holes we've found, like those in early quasars, may have even jump-started galaxy formation. Their intense radiation could have triggered the collapse of gas clouds, seeding the first stars and structures in the universe. It's a cosmic feedback loop. Black holes build galaxies, and galaxies feed black holes. And as we peer deeper into space, we're seeing this partnership in its infancy, revealing how the universe's grandest structures were forged. Up next, we'll zoom in on another mind-bending feature of these distant black holes: their ability to fire matter across the cosmos at nearly the speed of light. Now, let's shift our gaze to one of the most spectacular displays in the cosmos: the blistering jets erupting from distant black holes. These aren't just ordinary streams of matter, they're cosmic particle accelerators, launching material at speeds so close to light that the laws of physics start to bend. Imagine a beam of energy so powerful it could stretch across entire galaxies, visible billions of light years away. These relativistic jets, as scientists call them, are born from the chaos surrounding a supermassive black hole. As matter spirals into the black hole's accretion disk, not all of it gets swallowed. Some particles get funneled outward along the black hole's magnetic field lines, catapulted into space at nearly 99.9% the speed of light. That's so fast, a single jet could cross the distance from Earth to the Moon in less than 2 seconds. What's even more astonishing is how these jets defy time and distance. Because they're so energetic, they glow brightly in radio waves, X-rays, and even gamma rays, making them detectable across the universe. Some of the farthest jets we've observed, like those from the quasar PKS 1634+63, are so long they could span our Milky Way dozens of times over. But here's the real kicker. These jets aren't just cosmic fireworks. They shape their surroundings, heating interstellar gas and even preventing entire galaxy clusters from cooling. In a way, they're like cosmic sculptors, carving out voids and triggering or stifling star formation in their path. And as we study them, we're not just seeing a black hole's fury, we're witnessing the universe's most extreme particle physics lab in action. Up next, we'll turn the clock back to see how telescopes like Hubble first brought these distant black holes into focus. Now, let's take a moment to appreciate the trailblazer that first brought these distant cosmic giants into sharp focus: the Hubble Space Telescope. Before the James Webb Telescope and other advanced observatories took center stage, Hubble was our window into the early universe, uncovering secrets about black holes that rewrote astronomy textbooks. One of Hubble's biggest breakthroughs was confirming the existence of supermassive black holes at the hearts of nearly every large galaxy, but it didn't stop there. By peering deep into space, Hubble spotted quasars, the blazing beacons powered by black holes, so far away they existed when the universe was less than 1 billion years old. These discoveries proved that supermassive black holes weren't just common. They grew astonishingly fast in the cosmos' infancy. Hubble also gave us our first clear look at how these black holes shape their galaxies. It captured stunning images of jets and accretion disks, showing how black holes can heat surrounding gas, trigger star formation, or even shut it down entirely. And let's not forget Hubble's role in measuring the masses of distant black holes by tracking the dizzying speeds of stars orbiting them, a technique still used today. But perhaps Hubble's most underrated contribution was its ability to see through cosmic dust. While other telescopes struggled, Hubble's sharp vision revealed hidden black holes obscured by thick clouds of gas, proving they were more widespread than anyone guessed. Even now, as newer telescopes push further, Hubble's decades of data remain a goldmine for scientists piecing together the black hole puzzle. Up next, we'll see how the James Webb Telescope is building on Hubble's legacy to reveal even more about these ancient cosmic monsters. Now, let's turn our gaze toward the future, because the James Webb Space Telescope is about to rewrite the rules of black hole discovery. Unlike Hubble, which relied mostly on visible and ultraviolet light, Webb's infrared eyes can pierce through cosmic dust and gas like never before, revealing black holes hidden in the universe's earliest chapters. Imagine looking back to a time when the first galaxies were just assembling. Webb's sensitivity lets it detect the faint infrared glow of black holes so distant, their light has been stretched into invisibility by the expanding universe. This means we'll finally see black holes forming in the cosmic dark ages, a period Hubble could barely glimpse, but Webb's real game changer, its ability to study the chemical fingerprints around these ancient black holes. By analyzing the light from their accretion disks, Webb can uncover what these monsters were feeding on, whether it was primordial gas, shredded stars, or something even more exotic. That data could solve the biggest puzzle of all, how supermassive black holes grew so massive, so fast. And here's the kicker, Webb isn't just spotting black holes, it's mapping their neighborhoods. Its sharp images show how these gravitational giants influenced their infant galaxies, triggering or stifling star formation. Some theories even suggest early black holes acted like cosmic seeds around which entire galaxies took shape. Webb could prove it, so while Hubble laid the groundwork, Webb is the detective uncovering secrets we didn't even know to look for. Every new observation brings us closer to understanding how black holes shaped the universe, and perhaps how the universe shaped them. Now, let's unpack one of the most mind-bending tools astronomers use to measure the universe: redshift. When we talk about ULAS J1342+0928's staggering redshift of 7.54, we're essentially reading a cosmic odometer. Here's how it works. As light travels across the expanding universe, its wavelengths stretch, shifting toward the red end of the spectrum, like a siren's pitch dropping as an ambulance speeds away. The higher the redshift number, the farther and older the light source. A redshift of 7.54 means this black hole's light has been stretched to nearly 8 times its original wavelength by the time it reaches us. That places ULAS J1342+0928 a jaw-dropping 13.1 billion light-years away, showing us a snapshot of the universe when it was just 700 million years old. To put that in perspective, that's like glimpsing a baby photo of the cosmos taken before Earth even existed. But redshift isn't just about distance, it's a time machine. Every increment tells us how much the universe has expanded during the light's journey. So when Webb or other telescopes detect a higher redshift than this record breaker, we'll be peering back even closer to the Big Bang itself, uncovering black holes born in the universe's first breaths. Now let's shift our gaze to a cosmic showdown: black holes versus dark stars. While supermassive black holes are the undisputed heavyweights we observe across the universe, dark stars remain a fascinating what-if of astrophysics. Picture this: dark stars, if they existed, would be colossal, hypothetical objects powered not by nuclear fusion like regular stars, but by the annihilation of dark matter particles. They could have formed in the early universe, glowing faintly with heat but lacking the violent accretion disks and jets we associate with black holes. Here's the catch: despite decades of searching, we've found zero evidence for dark stars. Meanwhile, supermassive black holes are everywhere, lurking in galactic centers, powering quasars and bending spacetime with their sheer mass. The reason: black holes leave unmistakable fingerprints. Their gravitational pull tears matter apart, creating blazing accretion disks and spewing X-rays, while their event horizons cast shadows we can now image. Dark stars, by contrast, would be far quieter and nearly invisible, making them ghosts in the cosmic machine. So why do black holes dominate the scene? It boils down to survival of the fiercest. In the dense early universe, collapsing gas clouds likely birthed black holes directly, bypassing the dark star stage entirely. And once formed, black holes only grew hungrier, swallowing everything in their path. While dark stars remain a tantalizing idea, the universe seems to have bet on black holes, and their explosive, light-gobbling nature makes them impossible to ignore. This cosmic rivalry reminds us that sometimes the most extreme objects leave the loudest echoes across the universe. Now, let's pull back the curtain on how scientists unravel the mysteries of these ancient cosmic giants with the help of supercomputers. Imagine trying to recreate the universe's infancy, a time when matter was packed tightly and the first black holes began their reign. This isn't just a thought experiment. Supercomputers, with their staggering processing power, allow us to simulate these extreme conditions down to the smallest details. Here's how it works. Researchers feed these machines equations based on Einstein's theories, quantum mechanics, and the known laws of physics. Then, they set the clock back to just moments after the Big Bang, when the universe was a seething, dense soup of particles. The simulations track how tiny fluctuations in this primordial soup could have collapsed under gravity, forming the seeds of the first black holes. Some models suggest these seeds grew from massive gas clouds collapsing directly into black holes, skipping the star stage entirely. Others propose they formed from the remnants of the universe's first short-lived stars. What's truly mind-blowing is the scale of these simulations. They crunch numbers for millions or even billions of virtual particles, recreating cosmic environments over billions of years, all in a matter of days or weeks. Without supercomputers, we'd be left with mere speculation. But thanks to them, we can test theories, rule out impossibilities, and inch closer to understanding how the universe's most distant black holes came to be. So next time you hear about a distant black hole discovery, remember, it's not just telescopes doing the work. Supercomputers are the unsung heroes, painting a picture of the cosmos' wild early days. Now let's step into one of the universe's most transformative eras, the cosmic dawn. This was the moment when the first light sources, including those powered by distant black holes, began to pierce the darkness of the early cosmos. But their impact went far beyond illumination. These ancient black holes played a starring role in the epoch of reionization, a pivotal chapter that reshaped the universe itself. Here's why this matters. After the Big Bang, the universe was a fog of neutral hydrogen gas, blocking light from traveling freely. Then, around a few 100 million years later, something extraordinary happened. The first black holes, quasars, and stars flickered to life, flooding space with intense radiation. Their energy was so powerful that it stripped electrons from hydrogen atoms, turning the fog into a transparent sea of ionized gas, a process called reionization. What's fascinating is how these distant black holes turbocharged this cosmic makeover. Their quasars unleashed torrents of ultraviolet light, carving vast bubbles of ionized gas around them. Over millions of years, these bubbles overlapped, clearing the hydrogen fog and allowing light to travel across the universe for the first time. Without this cleanup crew, the cosmos would still be shrouded in darkness, and we'd see nothing beyond our own galaxy. But here's the twist. Scientists are still piecing together exactly how much black holes contributed versus the first stars. Some simulations suggest black holes did the heavy lifting, while others argue stars dominated early on. Either way, one thing's clear: these distant black holes didn't just lurk in the shadows. They helped switch on the lights for the entire universe, setting the stage for everything we see today. So when we study the most distant black holes, we're not just uncovering their secrets, we're tracing the very moment the cosmos woke up and began to shine. Now let's tackle one of the biggest head-scratchers in astrophysics, the sheer size of these ancient black holes. How did they grow so massive so fast? It's a puzzle that defies everything we thought we knew about black hole formation. Picture this. Some of the earliest supermassive black holes we've discovered weigh in at billions of times the mass of our Sun. But here's the catch: they existed when the universe was less than 1 billion years old. That's like finding a fully grown blue whale in a toddler's swimming pool. According to our current models, black holes just shouldn't have had enough time to bulk up that quickly. So how did they do it? One theory suggests these cosmic giants started as seed black holes, leftovers from the collapse of the universe's very first stars. But even then, they'd need to feast on matter at impossible rates to reach supermassive sizes so soon. Another wild idea: they might have formed directly from collapsing gas clouds in the dense early universe, skipping the star stage entirely. And then there's the feeding frenzy problem. Even if these black holes gorge themselves non-stop, the physics of their accretion disk should have put a speed limit on their growth. Too much matter crammed in too fast would have created radiation pressure, essentially blowing away their cosmic buffet before they could swallow it. Yet somehow they defied the odds. This isn't just a quirky cosmic mystery, it's a gaping hole in our understanding of black hole evolution. If these early giants didn't follow the rules, what else don't we know? Every time we spot another distant black hole, we're forced to rethink the textbooks, and that's what makes them so thrilling. They're not just ancient relics, they're cosmic rebels rewriting the story of the universe itself. But here's another cosmic question to chew on. What happened to these ancient black holes after all this time? Did they vanish, or are they still lurking out there, hidden in the depths of space? Let's think about it. The universe has aged over 13 billion years since these distant giants first formed. In that time, galaxies have collided, merged, and reshaped themselves countless times. So it's entirely possible that many of those early supermassive black holes have since smashed together, creating even larger monsters at the hearts of modern galaxies. Imagine two cosmic titans spiraling toward each other, their immense gravity warping space until boom, they become one. But here's the twist: some of these ancient black holes might still be out there unchanged. If they were in quieter corners of the universe, far from galactic collisions, they could have coasted through cosmic history undisturbed. We might even be looking at them right now without realizing it. Their light just hasn't reached us yet. Then there's the eerie possibility that some didn't survive. Black holes evaporate over unimaginable timescales thanks to Hawking radiation, but for the biggest ones, that process would take longer than the current age of the universe. So unless something exotic happened, like a collision with an even stranger cosmic object, they're probably still around. What's wild is that we might never know for sure. The farthest black holes we see are snapshots from the distant past, frozen in time. Their present-day fate is a mystery wrapped in the vastness of space. But one thing's certain: whether they've merged, faded, or grown even larger, these ancient giants have left their mark on the universe, and that mark is still shaping everything we see today. Now, let's turn our attention to something truly mind-blowing: the sheer power of the loudest quasars in the cosmos. These distant black holes aren't just massive, they're cosmic powerhouses blasting out energy at levels that defy imagination. Picture this: some of these quasars shine with the brightness of trillions of suns combined. That's not a typo, trillions. To put it in perspective, if our sun is a candle, these quasars are like a supernova exploding non-stop for millions of years. What fuels these extreme energy outputs? It all comes down to their insatiable appetites. As matter spirals into the black hole at nearly the speed of light, it heats up to millions of degrees, creating a swirling disk of superheated gas. This disk glows so intensely that it outshines entire galaxies. But the real spectacle happens when magnetic fields funnel some of that material into jets shooting outward at nearly light speed. These jets can stretch for hundreds of thousands of light years, lighting up the cosmos like interstellar lighthouses. The craziest part: we're seeing these quasars as they were billions of years ago, during the universe's most violent and energetic era. Back then, black holes had plenty of gas and stars to feast on, making their outbursts far more common and extreme than anything we see in the modern universe. Today, most supermassive black holes are relatively quiet, but these ancient quasars remind us of a time when the cosmos was a much louder, more chaotic place. And here's the kicker: even across such vast distances, the light from these quasars is so intense that it drowns out everything around them. Astronomers can spot them clear across the observable universe, using them as beacons to map the structure of space itself. So next time you look up at the night sky, remember, some of the faintest points of light out there might actually be the echoes of the loudest explosions the universe has ever seen. Now, let's shift gears to one of the most puzzling cosmic mysteries, the enigmatic cold spot in the cosmic microwave background. This strange, unusually cold region in the afterglow of the Big Bang has left scientists scratching their heads for years. Some theories suggest it could be the shadow of a distant supervoid, a vast empty region of space stretching over 1 billion light-years. But here's where it gets even wilder. Others propose it might be the imprint of an ancient, supermassive black hole lurking at the edge of the observable universe. Imagine the cosmic microwave background as a snapshot of the universe's infancy, a faint glow from when the cosmos was just 380,000 years old. Most of it is uniform, but this cold spot stands out like a cosmic bruise. If a supervoid is the culprit, its lack of matter would cause light passing through to lose energy, creating a cooler patch. But the sheer size needed to explain the cold spot pushes the limits of what we think is possible in the universe's structure. Then there's the black hole hypothesis. Some researchers speculate that a black hole from the very early universe, with a mass billions of times that of the Sun, could have warped spacetime so dramatically that it left a cold imprint on the cosmic microwave background. It's a radical idea, one that challenges our understanding of how black holes influence the large-scale cosmos. The debate is far from settled. While the supervoid explanation fits some observations, it doesn't fully account for the cold spot's extreme properties. The black hole theory, though tantalizing, lacks direct evidence. What's clear is that this cosmic anomaly forces us to rethink the limits of our models. Whether it's a void or a relic black hole, the cold spot reminds us that the universe still holds secrets waiting to be unraveled. And with next-generation telescopes, we might finally get the answers we've been searching for. Now, let's take a step even further back in time to the very first moments of the universe. One of the most fascinating ideas in cosmology is that some of the most distant black holes we see today might not have formed from collapsing stars or gas clouds at all. Instead, they could be ancient relics from cosmic inflation, that explosive expansion of spacetime just fractions of a second after the Big Bang. Picture this: the universe was smaller than an atom, hotter and denser than anything we can imagine, when suddenly it ballooned outward faster than the speed of light. During this chaotic stretch, tiny fluctuations in density could have collapsed into ultra-dense knots, primordial black holes. Unlike the black holes we know today, these wouldn't need stars or galaxies to form. They'd be born straight from the fabric of spacetime itself. What makes this theory so compelling is that it could solve multiple cosmic puzzles at once. Some scientists think these primordial black holes might even be the elusive dark matter we've been searching for. Others suggest they could explain why we see supermassive black holes so early in the universe's history, because they've been around since nearly the beginning. But here's the catch: we haven't found definitive proof yet. Primordial black holes would be incredibly hard to spot, especially if they're small. Some might have evaporated by now due to Hawking radiation, while others could be lurking unseen, weaving through galaxies like invisible ghosts. Future gravitational wave detectors or subtle distortions in the cosmic microwave background might finally reveal their presence. Whether they're out there or not, the idea ties black holes directly to the universe's birth, making them not just cosmic destroyers but potential time capsules from the dawn of everything. And if we ever confirm their existence, it would rewrite our understanding of how the cosmos grew from a fiery speck into the vast, structured universe we see today. Now, let's turn our attention to a cosmic mystery that's been puzzling astronomers for decades: the elusive missing link black holes. These are the intermediate mass black holes, lurking somewhere between the smaller stellar mass black holes formed from collapsing stars and the behemoth supermassive black holes that dominate galactic centers. Imagine a black hole weighing anywhere from a few hundred to a few 100,000 times the mass of our Sun. That's the sweet spot for these cosmic middleweights. They're not as common as their smaller or larger cousins, and spotting them has been like finding a needle in a galactic haystack. But why do they matter? Because they could hold the key to understanding how supermassive black holes grew so big so fast in the early universe. One leading theory suggests that intermediate mass black holes are the building blocks of supermassive ones. Picture this: in the chaotic early universe, these mid-sized black holes could have merged over time, gobbling up gas and stars to become the giants we see today. Some might even still be hiding in dense star clusters or the outskirts of galaxies, quietly waiting to be discovered. The hunt for these cosmic missing links has turned up a few promising candidates. Take HLX-1, for example, a bright X-ray source about 290 million light-years away, thought to be an intermediate mass black hole feasting on a nearby star. Then there's the bizarre object in the galaxy Messier 82, which flares with X-rays in a way that suggests it's far too massive to be a stellar black hole but not quite supermassive. But here's the twist: not all scientists agree these objects are truly intermediate. Some could be smaller black holes on a feeding frenzy, or even unusual stellar phenomena mimicking their behavior. The real breakthrough will come when we catch two of them merging, an event that would send gravitational waves rippling through space, detectable by observatories like LIGO or Virgo. Whether they're the missing piece of the black hole puzzle or just another cosmic oddity, intermediate mass black holes remind us that the universe still has plenty of secrets left to uncover. And if we can confirm their role in shaping the cosmos, it would fill a critical gap in our understanding of how black holes evolve, from the tiniest seeds to the monsters at the heart of galaxies. Now, let's talk about the hurdles we face when peering into the cosmic abyss. Studying black holes billions of light-years away isn't just difficult, it's like trying to read a book from across a football field while wearing foggy glasses. Our current technology, as impressive as it is, hits hard limits when observing these distant monsters. Take the Chandra X-ray Observatory, for instance. It's been revolutionary in detecting high-energy emissions from black holes, but even Chandra struggles when the light from these objects has traveled for over 13 billion years. By the time that faint signal reaches us, it's often drowned out by cosmic noise or stretched into near invisibility by the universe's expansion. Then there's the resolution problem. The most distant black holes appear as mere specks if they're visible at all. Even our sharpest telescopes can't discern details about their accretion disks or jet structures at such distances. It's like trying to study a grain of sand on a beach from orbit. But perhaps the biggest challenge is time itself. Observing these ancient black holes requires staring at the same patch of sky for hundreds, sometimes thousands, of hours to collect enough photons for analysis. Telescope time is precious, and there's only so much data we can gather before hitting physical limits of sensitivity. This is why next-generation telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are game-changers. With infrared capabilities far beyond Hubble's, they'll peer through cosmic dust and detect light stretched by the universe's expansion. Meanwhile, gravitational wave detectors like LISA may one day sense mergers from the universe's first black holes. The truth is, we're essentially trying to solve a 13 billion-year-old mystery with tools that are still in their cosmic infancy. But every technological leap brings us closer to understanding how these distant black holes shaped and continue to shape the story of our universe. Now, here's something that might surprise you: artificial intelligence is becoming astronomy's secret weapon in the hunt for the universe's most elusive black holes. With mountains of data pouring in from telescopes every night, scientists are turning to machine learning to spot the needles in this cosmic haystack. Imagine sifting through millions of faint blips in the sky, trying to find the handful that might be supermassive black holes from the dawn of time. That's where AI steps in. Algorithms trained on known black hole signatures can scan vast datasets in seconds, flagging potential candidates that human eyes might miss. They're not replacing astronomers, they're supercharging them. One breakthrough came when researchers fed AI systems simulated data of early universe black holes. The algorithm learned to recognize subtle patterns in the light, like how a seasoned detective spots clues at a crime scene. Soon after, it identified real candidates in old telescope archives that had been overlooked for years. But the real game changer, AI's ability to predict where we should look next. By analyzing the distribution of known distant black holes, machine learning models can pinpoint regions of the sky most likely to hide others. It's like having a treasure map for the cosmos. Of course, AI isn't perfect. These systems still need human oversight to weed out false positives, cosmic mirages that trick the algorithm. Yet as the data grows and the tech improves, one thing's clear. The future of black hole discovery will be a partnership between human curiosity and machine precision. And who knows, the next record-breaking distant black hole might be lurking in plain sight, waiting for the right algorithm to uncover it. Now, let's venture into one of the most mind-bending ideas in modern cosmology, the phantom black hole hypothesis. Picture this: what if some of the universe's most massive black holes aren't just hiding in the distant corners we can see, but exist entirely beyond the edge of our observable universe? It sounds like science fiction, but some theorists argue it's a real possibility. The observable universe is the portion of space we can detect, limited by how far light has traveled since the Big Bang about 13.8 billion years ago. But the full universe might be infinitely larger, meaning there could be regions forever out of our view. If black holes exist in those unseen realms, they'd be invisible to us, yet their gravitational influence might still leave subtle fingerprints on the cosmos we can observe. One wild theory suggests these phantom black holes could be remnants of a previous cosmic cycle, leftover giants from a universe that existed before ours. Others propose they're the seeds of entirely separate bubble universes, hidden beyond our cosmic horizon. While we can't directly detect them, their gravity might subtly warp the fabric of space-time near the edges of our observable universe, like shadows cast from another dimension. Of course, this is all speculative, there's no direct evidence yet. But if future telescopes spot unexplained gravitational anomalies or strange distortions in the cosmic microwave background, it might just hint at these invisible giants lurking in the darkness beyond. And that raises an even bigger question. If black holes exist outside our cosmic backyard, what else is out there waiting to be discovered? Now, let's take a step even deeper into the cosmic unknown, where the bizarre world of quantum mechanics meets the colossal scale of black holes. Imagine the universe in its earliest moments, a seething, chaotic sea of energy where space itself was a bubbling froth of quantum fluctuations. This so-called quantum foam wasn't just empty noise, it might have been the birthplace of the very first black holes. Here's how it could have happened. In those first fractions of a second after the Big Bang, tiny pockets of space could have randomly collapsed under their own gravity, thanks to extreme density variations in the quantum foam. These microscopic black holes, some no larger than a single atom, might have formed in vast numbers. Most would have evaporated almost instantly, as Stephen Hawking predicted. But a rare few could have survived, growing over billions of years into the supermassive monsters we see today at the centers of galaxies. Some theorists take this idea even further. If these primordial black holes did form, they might not just be lurking in the distant cosmos, they could be all around us, even in our own solar system, too small and dark to detect. Some scientists have even suggested they could explain the mystery of dark matter, though that's still hotly debated. Of course, this is all theoretical. No one has ever observed a primordial black hole. But if future experiments or telescopes ever spot one, it would revolutionize our understanding of both black holes and the quantum origins of the universe itself. And that leaves us with a tantalizing thought. What if the seeds of the universe's most distant giants were planted not by collapsing stars, but by the random flickers of space-time itself? Shifting our gaze from the quantum origins of black holes, let's tackle one of the most perplexing puzzles in physics, the black hole information paradox. This mind-bending conundrum, first highlighted by Stephen Hawking, challenges our very understanding of reality. Here's the crux of it. According to quantum mechanics, information about particles, their properties, their states, can never truly be destroyed. But black holes, with their relentless gravitational pull, seem to violate this rule. When matter falls into a black hole, it's gone forever, or so we once thought. Hawking's work suggested that black holes slowly evaporate over time, radiating away energy in what we now call Hawking radiation. But here's the catch: if the black hole vanishes, what happens to all the information it swallowed? Distant black holes, especially those from the universe's infancy, might hold unexpected clues. Their extreme environments could preserve subtle imprints of the information they've consumed, encoded in ways we're only beginning to theorize. Some scientists speculate that the answer lies in the holographic principle, the idea that all the information inside a black hole might be projected onto its event horizon like a cosmic fingerprint. Others suggest that distant black holes, with their unique formation histories, could reveal new physics that bridges the gap between quantum mechanics and gravity. While we're still far from solving this paradox, each distant black hole we study is like a time capsule, potentially hiding the keys to one of physics' greatest mysteries. And if we ever crack it, we won't just understand black holes better, we might unlock the deepest secrets of the universe itself. Now, let's take a step into one of the most radical ideas in modern physics, the holographic principle. Imagine the entire universe with all its galaxies, stars, and even the most distant black holes as nothing more than a projection, like a hologram. This mind-bending concept suggests that all the information in a three-dimensional space like the interior of a black hole might actually be encoded on a two-dimensional surface, such as its event horizon. Distant black holes play a starring role in this theory. Their immense gravity warps spacetime so severely that they could act as natural laboratories for testing the holographic principle. Think of it like this: everything that falls into a black hole, every star, every particle leaves an imprint on its boundary, much like how a hologram stores a 3D image on a flat surface. Some physicists believe this could mean our entire universe operates the same way, with reality itself being a kind of cosmic projection. What makes this even more fascinating is how it ties into the black hole information paradox we just discussed. If information isn't lost but instead smeared across the event horizon, the holographic principle could be the key to resolving one of physics' biggest mysteries. And the most distant black holes, those ancient giants from the dawn of time, might hold the clearest evidence. Their sheer size and age could reveal whether the universe truly is a hologram, or if we're just scratching the surface of an even deeper truth. So the next time you look up at the night sky, remember, the cosmos might not be as three-dimensional as it seems. Those distant black holes could be whispering a secret, that reality itself is far stranger and far more interconnected than we ever imagined. Now, let's stretch our imaginations even further. What if those distant black holes aren't just cosmic oddities, but gateways to entirely different universes? The multiverse theory, a hot topic in modern physics, suggests our universe might be just one of countless others, each with its own laws and realities. And here's where black holes come in. Some scientists speculate that the extreme warping of spacetime near a black hole's singularity could create a bridge, a wormhole, to another universe. Think of it like a cosmic tunnel. If you could somehow survive the trip through a black hole, you might not emerge in the same universe you started in. The most distant black holes, those ancient behemoths from the universe's infancy, could be the best candidates for this wild possibility. Their sheer size and age mean they've had billions of years to stabilize, potentially forming stable wormholes instead of chaotic singularities. Of course, this is all theoretical, no one sending probes into black holes anytime soon. But the math doesn't rule it out. In fact, some models of the multiverse suggest that black holes could be natural byproducts of collisions between universes in a vast, bubbling cosmic foam. If that's true, then every distant black hole we observe might be a scar from a long-ago clash of realities. So while we can't say for sure whether black holes are multiverse portals, the idea forces us to ask bigger questions. Are we alone in existence, or is our universe just one page in an infinite cosmic library? Those distant black holes glowing faintly at the edge of time might hold the answer if we ever learn to read their secrets. Now, let's take a step back and connect this mind-bending idea to one of astronomy's biggest puzzles, the Fermi paradox. If the universe is so vast and ancient, why haven't we found any signs of advanced civilizations? One intriguing possibility ties directly to those distant black holes. Imagine a civilization so advanced that it doesn't just observe black holes but harnesses their energy. Think about it, black holes are the ultimate power sources. Their accretion disks glow with unimaginable energy, and their gravitational pull could be tapped for propulsion or even computation. A civilization mastering this technology might not need planets or stars anymore. They could live near black holes, invisible to our telescopes, drawing energy from these cosmic engines. This could explain the eerie silence of the universe. Instead of broadcasting radio signals or building megastructures we can detect, advanced beings might have moved beyond traditional technology. They could be operating on scales we can't even perceive, using black holes as their playgrounds. The most distant black holes, with their immense energy outputs, would be prime real estate for such civilizations. Of course, this is speculative, but it's a fascinating twist on the Fermi paradox. Maybe we're not hearing from aliens because they've graduated to a black hole-based existence, leaving the rest of the universe behind. And if that's true, those faint, ancient black holes at the edge of our vision might not just be relics of the cosmos, they could be someone's home. Now, shifting our gaze from cosmic mysteries to groundbreaking achievements, let's talk about one of humanity's most astonishing feats, the first ever image of a black hole's shadow. In 2019, the Event Horizon Telescope, a global network of radio telescopes, captured history by revealing the silhouette of the supermassive black hole at the heart of galaxy M87. This wasn't just a blurry smudge, it was a glowing ring of light bending around the black hole's event horizon, a direct snapshot of gravity warping space-time itself. The technique behind this breakthrough, called very long baseline interferometry, combines data from telescopes scattered across the globe to create a virtual dish as wide as Earth. This lets astronomers achieve unprecedented resolution, sharp enough to spot a donut on the moon. While M87's black hole is relatively close at 55 million light-years away, the same method could one day peer deeper into the cosmos. Imagine pointing this cosmic camera at the universe's most distant black holes, those ancient giants like ULAS J1342+0928. Of course, the farther we look, the tougher the challenge. Distant black holes appear tinier in the sky, and their light is stretched and dimmed by cosmic expansion. But with next-generation telescopes and even space-based arrays, we might eventually glimpse the shadows of these primordial monsters. Each one would be a time capsule, showing us not just a black hole, but the universe as it looked billions of years ago. The Event Horizon Telescope's first image was just the beginning. The next frontier is staring into the abyss at the edge of time itself. Now, let's turn our attention to one of the most visually stunning features of these cosmic giants, the fiery rings that surround them. Picture this, a supermassive black hole, billions of light-years away, doesn't just lurk in darkness. Instead, it's often encircled by a blazing disk of gas and dust spinning at nearly the speed of light. This is the accretion disk, often nicknamed the Ring of Fire, and it's one of the most extreme environments in the universe. The temperatures here are mind-bending. As matter spirals inward, friction and intense gravitational forces heat it to millions of degrees, causing it to glow fiercely across the electromagnetic spectrum. In some cases, these disks outshine entire galaxies, making them visible across cosmic distances. The innermost regions can reach temperatures so high that atoms are torn apart, creating a swirling soup of charged particles. What's even more fascinating is how these disks behave. They're not uniform. Some sections flare unpredictably, while others eject colossal jets of energy. For the most distant black holes, studying their accretion disks is like peering into a time machine. The light we see today left those disks when the universe was just a fraction of its current age, offering clues about how black holes fed and grew in the cosmos's infancy. And here's the kicker: without these glowing rings, many distant black holes would remain invisible. It's their fiery embrace that betrays their presence, turning them from cosmic ghosts into beacons we can study. So next time you hear about a black hole discovery, remember, it's often the Ring of Fire that lights the way. Now, let's bend our minds with one of Einstein's most astonishing predictions. Time itself warps near these distant black holes. Imagine standing close to one of these cosmic monsters. While only a few minutes might pass for you, centuries could fly by on Earth. This bizarre phenomenon is called time dilation, and it's a direct consequence of the black hole's immense gravity warping the fabric of space-time. The closer you get to the event horizon, the point of no return, the more extreme this effect becomes. Light struggling to escape the black hole's pull stretches into longer wavelengths, a process called gravitational redshift, while time slows to a crawl. For a supermassive black hole billions of light years away, this means that if we could observe a clock near its edge, it would tick infinitely slower than one here on Earth. Here's where it gets even wilder. If a star were to orbit very close to such a black hole, an outside observer would see its light dim and redden as time for the star appears to freeze. Yet from the star's perspective, time would feel normal. This isn't science fiction, it's the universe obeying relativity's strict rules. And for those distant black holes we've been discussing, their time dilation effects are magnified by their sheer distance. The light we see from their surroundings left when the universe was young, meaning we're glimpsing events that unfolded in extreme slow motion, frozen in the distant past. It's a cosmic reminder that time isn't just a ticking clock. It's a flexible, stretchable dimension shaped by gravity's invisible hand. Now, let's listen to the whispers of the cosmos, because black holes don't just warp time, they leave behind ghostly echoes. Scientists have detected something extraordinary around distant black holes: delayed light echoes, like cosmic ripples bouncing off their chaotic surroundings. Here's how it works. When a black hole devours matter, it doesn't do it quietly. The material spiraling into its grasp heats up to millions of degrees, blasting out X-rays. But sometimes these X-rays don't reach us directly. Instead, they bounce off clouds of gas swirling around the black hole, creating a delayed echo that arrives years, even decades later. It's like hearing a shout reverberate through a cavern long after the sound was made. These echoes aren't just cosmic curiosities, they're treasure maps. By studying them, astronomers can map the turbulent environments near these distant black holes, revealing details about the structure of their accretion disks and the violent storms of radiation they unleash. Some echoes even hint at hidden features like warped disks or towering jets of plasma that would otherwise stay invisible. And here's the wild part: because these black holes are so far away, their echoes are ancient. The light we're catching now left when the universe was a fraction of its current age, meaning we're essentially eavesdropping on black hole tantrums from billions of years ago. It's a stark reminder that even the most distant corners of the cosmos still find ways to speak to us if we're patient enough to listen. Next up, we'll see how these distant black holes aren't just isolated monsters but key players in the universe's grand architecture woven into the cosmic web itself. Now let's zoom way out to see how these distant black holes fit into the universe's grand design. Picture the cosmos as a vast, intricate spiderweb with galaxies strung along shimmering threads of gas and dark matter. This is the cosmic web, the scaffolding of the universe, and guess what sits at its busiest intersections? Supermassive black holes acting like cosmic anchors. These black holes aren't just lurking in isolation, they're powerhouses at the heart of galaxy clusters, where the universe's largest filaments meet. Think of them as gravitational glue holding entire neighborhoods of galaxies together. The energy they unleash through jets and radiation can even shape the web itself, heating up surrounding gas and preventing it from collapsing into new stars. But here's the twist: the cosmic web isn't static. It's a dynamic, ever-evolving structure, and distant black holes play a starring role in its growth. Their gravity pulls matter into dense knots, while their explosive deaths through mergers or jets can send shockwaves rippling through the web, redistributing matter across billions of light years. It's a cosmic tug-of-war, with black holes as both architects and wrecking balls. And because the most distant black holes formed when the universe was young, studying them lets us peek at the cosmic web in its infancy. Their positions reveal how the universe's large-scale structure took shape, like fossils of the universe's teenage years. So next time you hear about a distant black hole, remember, it's not just a monster in the void. It's a thread in the universe's tapestry, weaving the story of everything. Coming up, we'll explore how high-energy particles from these black holes might be sending secret messages all the way to Earth through ghostly cosmic neutrinos. Now, let's shift our gaze from the vast cosmic web to something far smaller yet just as mysterious. Imagine particles so tiny and elusive they pass through entire planets like ghosts. These are neutrinos, and they might hold secrets about the universe's most distant black holes. Here's the wild part: some of the highest energy neutrinos ever detected on Earth could be cosmic postcards from supermassive black holes billions of light years away. How, when these black holes unleash their powerful jets, streams of particles racing at nearly the speed of light collisions within those jets might produce neutrinos. These particles, unlike light, don't get scattered or absorbed as they travel. They zip straight through space undisturbed until they reach detectors buried deep in Antarctic ice or underwater observatories. But why does this matter? Because neutrinos give us a backstage pass to the most violent events in the universe. Light can be blocked or distorted by dust and gas, but neutrinos deliver unfiltered intel. When we trace one back to its origin, it could point directly to a distant black hole's jet, helping us map where these cosmic monsters are wreaking havoc. And there's more. Some neutrinos arrive with energies 1,000,000 times higher than those produced in particle colliders on Earth. That means the black holes firing them off must be engines of unimaginable power. It's like finding a fingerprint at a crime scene, only this fingerprint was blasted across the cosmos by a supermassive black hole's fury. So next time you hear about a neutrino detection, remember, it might be a whisper from one of the universe's most distant giants telling us where to look next. Up ahead, we'll tackle another puzzle: how these ancient black holes could be shaping the very fabric of space itself. Now, let's turn our attention to one of the biggest mysteries in cosmology: dark energy. This invisible force is causing the universe to expand faster and faster, yet we still don't fully understand what it is. But here's where distant black holes come in. Their growth rates might hold clues to dark energy's influence on the cosmos. Think of it like this: supermassive black holes in the early universe grew to staggering sizes incredibly fast. Some theories suggest that dark energy, which permeates all of space, could have played a role in how these black holes consumed matter and expanded. If dark energy was stronger in the past, it might have altered the way gas and dust collapsed into black holes, accelerating their growth in ways that defy our current models. But here's the twist. If we can measure the growth rates of ancient black holes and compare them to predictions, any discrepancies could hint at dark energy's behavior over cosmic time. It's like finding a hidden pattern in the universe's expansion, one that only these distant giants can reveal. And there's another layer. Some scientists speculate that dark energy and black holes might be more deeply connected than we realize. Could the energy released by these black holes somehow feed into the dark energy driving the universe apart? Or does dark energy create the perfect conditions for black holes to thrive? Right now, it's all speculation, but studying the most distant black holes could bring us closer to answers. So while dark energy remains elusive, these cosmic behemoths at the edge of the observable universe might just hold the key to unraveling its secrets. Up next, we'll explore a curious lull in black hole activity, a cosmic drought that has scientists scratching their heads. Now, here's something that might surprise you. Even in the chaotic early universe, black holes didn't always feast at full speed. There were times when their activity mysteriously dropped off, a cosmic drought that left scientists puzzled. Imagine the universe as a bustling city where black holes are the busiest restaurants, constantly devouring matter. But then, suddenly, some of these cosmic diners closed their doors for a while. Around 9 billion years ago, astronomers noticed a strange slowdown in quasar activity, the bright beacons powered by supermassive black holes. For reasons we still don't fully understand, these monsters seem to stop feeding as aggressively and their brilliant glow dimmed. One theory suggests that during this lull, the surrounding gas and dust, the fuel for black holes, became scarcer. Maybe the universe's expansion stretched resources too thin, or perhaps something disrupted the flow of matter into these cosmic pits. Another idea points to changes in galaxy collisions, which often trigger black hole growth. If galaxies stopped merging as frequently, the black holes inside them might have gone hungry. But here's the kicker: this drought wasn't universal. Some black holes kept feasting while others went quiet, adding another layer of mystery. Studying these quiet periods helps us piece together how black holes and their galaxies evolve over time, and why the universe sometimes hits the brakes on its most violent phenomena. Up next, we'll dive into the hunt for the first direct evidence of ancient black hole collisions, a discovery that could rewrite cosmic history. Now, let's turn our attention to a cosmic detective story that's still unfolding. Gravitational wave detectors like LIGO and Virgo have already revolutionized our understanding of black hole collisions closer to home. But what if these incredible machines could pick up whispers from the universe's very first black hole mergers? Think of gravitational waves as ripples in a pond, only this pond is spacetime itself. When two black holes collide, they send out these ripples, traveling across the cosmos for billions of years. So far, we've detected mergers from black holes that formed relatively recently in cosmic terms. But scientists are racing to tune these detectors to catch signals from the earliest collisions, ones that happened when the universe was just a toddler. Here's why that's so exciting. The first black hole mergers could reveal how these giants grew so big so fast. Were they born massive, or did they balloon by devouring everything around them? Did they collide frequently in the crowded early universe, or was it a rare event? Each gravitational wave from these ancient crashes would carry clues about the conditions of the cosmos back then, like a time capsule encoded in space-time. The challenge: these waves would be incredibly faint after their journey across 13 billion years. But next-generation detectors, like the planned Laser Interferometer Space Antenna LISA, could be sensitive enough to hear them. Imagine the thrill if we one day capture the faint echo of two primordial black holes locking in a death spiral, a dance that began when galaxies were just starting to form. This isn't just about adding to our list of cosmic discoveries. It's about unlocking the origin story of the universe's most mysterious objects. And with every upgrade to our gravitational wave technology, we get closer to rewriting the first chapters of black hole history. Coming up, we'll explore another puzzle, the powerful magnetic fields around these distant black holes, and why they defy everything we know about physics. Now, let's unravel one of the most baffling enigmas surrounding these cosmic giants, their magnetic fields. Picture a black hole so distant, its light has traveled nearly the entire age of the universe to reach us. Yet, what's even more astonishing than its distance is the sheer power of the magnetic fields swirling around it. These aren't just strong, they're strong enough to twist the rules of physics as we know them. Here's the puzzle. Magnetic fields around black holes are generated by their accretion disks, the superheated plasma spiraling into the abyss. But the fields we've detected around some of the most distant black holes are orders of magnitude more intense than our models predict. They're so powerful they can launch jets of particles at nearly the speed of light, shooting across thousands of light years. The problem: our current understanding of plasma physics can't fully explain how these fields grow so strong or how they remain so stable over cosmic timescales. One theory suggests turbulence in the accretion disk amplifies these fields, like a whirlpool stirring up chaos. Another idea points to the black hole's spin, a rotating monster acting like a dynamo, cranking up the magnetic energy to extreme levels. But neither theory fully accounts for the jaw-dropping strengths we observe. It's as if these black holes have a secret recipe for magnetism that we haven't cracked yet. What makes this even wilder is that these magnetic fields might hold the key to understanding how black holes shape their galaxies. They can funnel matter into the black hole's maw or fling it outward, influencing star formation and galactic evolution billions of light years away. Yet, despite their importance, they remain one of the least understood aspects of black hole behavior. As we push our telescopes and simulations to new limits, each discovery peels back another layer of this mystery. And with every layer, we're forced to rethink what we know about the fundamental laws governing the cosmos. Up next, we'll tackle an even more radical question. What if some of these distant black holes don't have event horizons at all? A concept that could turn astrophysics on its head. Now, let's venture into one of the most mind-bending ideas in black hole physics. What if some of these distant cosmic monsters don't have event horizons at all? Imagine a black hole stripped bare, its singularity exposed to the universe without the usual point of no return. This wild concept, known as a naked singularity, would defy everything Einstein's theory predicts about how black holes should behave. Here's why this idea shakes up astrophysics. According to classical general relativity, every black hole must hide its singularity behind an event horizon, the boundary where gravity becomes so strong that not even light can escape. It's like a cosmic curtain shielding the universe from the chaos inside. But what if that curtain doesn't exist? A naked singularity would mean we could, in theory, observe the raw, unfiltered core of a black hole, where the laws of physics as we know them break down completely. The problem: no one's ever found definitive proof of one. Most observations align with black holes having event horizons, but some distant, hyperactive black holes behave in ways that make scientists wonder. For instance, certain quasars, those ultra-bright beacons powered by supermassive black holes, flare up with energy patterns that don't quite fit the standard model. Could these be glimpses of naked singularities, or just extreme versions of normal black holes? The debate splits physicists. Some argue that if naked singularities exist, they'd be so unstable they'd instantly collapse into a traditional black hole. Others suggest that under extreme conditions like the intense environment of the early universe, these cosmic oddities might have formed and persisted. There's even a tantalizing link to quantum gravity theories, where the rules of the very small might allow singularities to exist without event horizons. If proven real, naked singularities wouldn't just rewrite textbooks, they'd force us to rethink gravity itself. They could be portals to new physics, revealing secrets about space-time that have eluded us for centuries. Until then, they remain one of the most thrilling what-ifs in the study of distant black holes. Next up, we'll explore another cosmic spectacle, the high-speed plasma bullets some black holes fire across the universe, leaving trails of destruction in their wake. Now, let's shift our gaze to one of the most violent phenomena in the cosmos, black holes firing high-speed plasma bullets across the universe. Picture this: supermassive black holes at the edge of the observable universe don't just sit quietly. Some of them act like cosmic railguns, launching massive clumps of superheated plasma at nearly the speed of light. These aren't just tiny sparks, they're colossal projectiles, sometimes as large as entire solar systems, tearing through intergalactic space for millions of light years. What powers these extreme eruptions? It all comes down to the chaotic environment around a black hole's accretion disk. As matter spirals inward, magnetic fields twist and snap, channeling some of that material into narrow, ultra-fast jets. But occasionally, instability kicks in, and instead of a smooth jet, the black hole hurls out dense, cannonball-like blobs of plasma. These bullets carry unimaginable energy, enough to outshine entire galaxies for brief moments. The aftermath is just as dramatic. When these plasma bullets slam into surrounding gas clouds or even other galaxies, they trigger shock waves that heat intergalactic material to millions of degrees. Astronomers have spotted the scars of these collisions, enormous cavities in galaxy clusters, carved out by the sheer force of the impact. Some of the most distant black holes we've observed seem to be repeat offenders, firing volleys of these projectiles over cosmic timescales. Why does this matter? These violent outbursts aren't just cosmic fireworks. They play a crucial role in shaping the universe's large-scale structure. By redistributing energy and matter across vast distances, black hole bullets help regulate star formation, heat up galactic neighborhoods, and even determine where future galaxies can form. Without them, the cosmos might look entirely different. Up next, we'll dig into another cosmic clue: how distortions in the universe's oldest light might reveal hidden populations of black holes lurking in the shadows. Now, let's turn our attention to the universe's oldest light, the cosmic microwave background. This faint glow, left over from the Big Bang, is like a cosmic fingerprint, holding secrets about the earliest moments of existence. But here's the twist: subtle distortions in this ancient light might be pointing us toward hidden black holes lurking in the distant cosmos. When we map the cosmic microwave background, we expect it to be smooth, a near-perfect snapshot of the infant universe. Yet, certain patches appear slightly warped, as if something massive is bending the light on its way to us. One leading explanation: invisible supermassive black holes, too distant or dim to detect directly, could be distorting the background radiation through their immense gravity. It's like finding hidden objects by the shadows they cast. These distortions, called secondary anisotropies, are tiny but telltale. Some could be caused by black holes heating surrounding gas during the universe's formative years, creating hotspots in the cosmic microwave background. Others might stem from black holes warping space-time so severely that they act as cosmic lenses, subtly twisting the light's path over billions of years. What makes this so groundbreaking is the scale. If confirmed, these clues could reveal black holes that formed before the first galaxy's primordial giants, hiding in plain sight. They'd fill gaps in our understanding of how the universe's structure emerged and why some regions of space seem oddly empty. Up next, we'll explore an even wilder idea. Could some dark matter actually be the ancient remnants of black holes that evaporated long ago? The cosmic detective work continues. Now, let's venture into one of the most intriguing cosmic mysteries. Could dark matter, the invisible glue holding galaxies together, actually be the ghostly remains of long-dead black holes? Here's the puzzle. Dark matter makes up roughly 27% of the universe, yet we've never directly detected it. scientists have proposed countless candidates from exotic particles to hidden dimensions. But one theory stands out for its elegance. What if dark matter is made of black hole fossils? Primordial black holes, hypothetical objects thought to have formed in the chaos of the early universe, could be the key. Unlike the black holes we know today, these wouldn't have come from collapsing stars. Instead, they'd be born from dense patches of matter moments after the Big Bang. Some might have been as small as asteroids, others as massive as planets. Over time, the tiniest ones would have evaporated completely, thanks to Hawking radiation, leaving behind nothing but whispers of their existence. But here's the twist: if these primordial black holes were just the right mass, they might not have fully evaporated. Instead, they could have left behind ultra-dense remnants, smaller than an atom yet heavier than a mountain. These relics would be invisible, barely interacting with light or matter, just like dark matter. The implications are staggering. If true, it would mean the universe's missing mass isn't some exotic particle but the ashes of ancient black holes lingering since the dawn of time. It's a cosmic irony. The darkest entities in space might solve the darkest mystery in physics. Up next, we'll peer even further into the future, asking what becomes of supermassive black holes as the universe ages toward its final act. Now let's fast forward trillions of years into the future, where even the mightiest black holes face their inevitable fate. Picture this: as the universe keeps expanding, galaxies drift farther apart, stars burn out, and cosmic darkness creeps in. But what happens to the supermassive black holes that once ruled the centers of galaxies? Here's the startling truth: over unimaginable timescales, even these colossal giants won't last forever. Thanks to Hawking radiation, black holes slowly lose mass, emitting tiny particles until they eventually evaporate. For a typical supermassive black hole, this process would take longer than the current age of the universe, around 10 to the power of 100 years. That's a 1 followed by 100 zeros, but here's where it gets eerie. As the universe expands, accelerating due to dark energy, matter becomes so scattered that black holes can no longer feed. Starved of new material, they'll sit in isolation, growing colder and quieter. The last light in the cosmos might not come from stars, but from the faint glow of evaporating black holes, a final whisper before complete darkness. And what remains after they're gone? Only echoes. Any information swallowed by these black holes could be lost forever, or perhaps encoded in some mysterious way we don't yet understand. It's a humbling thought: the universe's most powerful engines reduced to nothingness over eternity. Up next, we'll tie it all together, exploring why these distant black holes hold the keys to the universe's deepest secrets, and why they matter more than we ever imagined. Now, let's bring it all together. Why do these ancient, distant black holes hold such profound significance? It's not just about their staggering size or mind-bending distances. These cosmic giants are like time capsules, preserving clues about the universe's earliest moments. By studying them, we're piecing together a puzzle that stretches back to the Big Bang itself. Think of it this way: every distant black hole is a snapshot of the universe in its infancy. Their sheer existence challenges our theories about how quickly structures formed after the birth of the cosmos. How did they grow so massive, so fast? The answers could rewrite our understanding of gravity, dark matter, and even the fabric of space-time, but it goes deeper. These black holes are laboratories for testing the extremes of physics. Their intense gravity bends light, warps time, and pushes the limits of Einstein's theories. By observing them, we're not just exploring the past, we're uncovering universal laws that govern everything from the smallest particles to the largest galaxies. And perhaps most importantly, they remind us of our place in the cosmos. In a universe filled with unfathomable scales and mysteries, studying these distant black holes connects us to the grand story of existence. They're not just relics of the past, they're keys to understanding where we came from and where the universe might be headed. So the next time you gaze at the night sky, remember, those faint points of light aren't just stars. Somewhere out there, the universe's oldest black holes are still whispering their secrets, and we're just beginning to listen. If you've made it this far, you're clearly as fascinated by these cosmic mysteries as we are. Don't forget to hit like, subscribe, and ring that notification bell so you never miss our deep dives into the universe's greatest wonders. Drop a comment below. What's the most mind-blowing fact you learned today? Until next time, keep looking up. From the farthest reaches of the cosmos to the edges of our understanding, we've journeyed through 50 astonishing facts about the universe's most distant black holes. We've uncovered how these ancient giants defy expectations, from their rapid growth just after the Big Bang to their role as cosmic lighthouses, illuminating the darkest corners of space. We've explored the cutting-edge tools that let us peer billions of years into the past, and the mind-bending physics that still leaves scientists scratching their heads. Yet for every answer, a dozen new questions emerge. How did these black holes grow so massive so quickly? What secrets do their jets and accretion disks hold? Could they even be windows into other dimensions or clues to dark matter's true nature? The universe, it seems, loves keeping us on our toes. That's the beauty of cosmic exploration. Every discovery pulls back another layer of the mystery. Whether you're a seasoned space enthusiast or just dipping your toes into the wonders of astronomy, these distant black holes remind us that curiosity is our greatest tool. The more we learn, the more we realize how much is still out there waiting to be uncovered. So keep that sense of wonder alive. The next breakthrough could be just over the horizon, and who knows, maybe one day you'll be the one connecting the dots in this grand cosmic puzzle. If this journey through space's deepest mysteries left you awestruck, don't forget to hit like and subscribe. Your support helps us keep exploring the universe's biggest questions. Drop a comment below which fact blew your mind the most. Until next time, stay curious and keep looking up.